For our first lesson in probability, we're going to talk about the definitions of theoretical probability and experimental probability. Something to keep in mind is the word theoretical does have the word theory in it. Okay, so in theory, meaning we're going to talk about kind of a prediction or an idea based on facts. So theoretical probability, we need to think about is like what should happen. Okay, should being a key word here. What we expect. For instance, when you flip or when you roll a six-sided die, you would expect to roll a 3 1/6 of the time. Now, experimental probability is what actually happens when you do the experiment. So we could roll a die, and you could roll it 6 times and never even get a 3, and you could roll it 20 times and never even get a 3. That's not what should happen. It's not what we expect to happen, but it actually can happen that way when you are doing an experiment. So what actually happens? Okay, so now it is possible to have your experimental probability match your theoretical probability. That is possible. If I roll a six-sided die 6 times, it is possible to get a 3 to show up once. That is possible. So we think it should happen, but it doesn't always happen. But it is possible for these two to match. So a proportion can be used to predict the number of times an event will occur based on its theoretical probability. So a spinner has 5 equally sized sections labeled 1 through 5. So I'm going to draw my spinner. Okay, just like this. I'm going to label them 1 through 5. So here's 1, 2, 3, 4, and 5. If the spinner is spun 60 times, predict the number of times the spinner will land on section 1. Well, section 1 would just be 1 out of 5 times. And we want to know how many times out of 60. Okay, so we set up this proportion. So 1 out of 5 times it's going to land on 1. So how many times out of 60? Okay, so now we cross multiply. So we get 5x equals 60. And we divide both sides by the coefficient, which is 5. So I get x is equal to 12 times. So I could expect for the spinner to land on section 1 about 12 times, but I wouldn't expect it to land on it exactly 12. Okay, again, this is just a prediction. Or my theoretical probability. Okay, this is my theoretical probability. So it should happen about 12 times. Again, this is just a prediction. So about 12 times is going to be my answer. Okay, so don't worry about the numbers here. Let's just look at the examples. Jamie took 20 pieces of colored paper and put them in a hat. 8 pieces were red. So I'm going to make a little list here. I'm going to say red, 8. 3 were blue, so I'm going to say blue is 3. And the rest were green. So, I have green, and 8 plus 3 is 11. So 20 minus 11 is 9. So the rest were green, so 9 are green. Okay, she pulls a piece of paper out of the hat. What are the chances that the paper is red? Well, how many red do I have? I have 8 red out of 20 altogether. So that's my probability. However, I can simplify this. So I'm going to divide this by 4. Divide this by 4. And I'm going to get 2/5. I'll go ahead and make that 5 look a little bit better there. So 2/5 is my probability of drawing a red piece of paper. Okay, the next one, a spinner was spun 32 times. The results are shown in the table below. Okay, so 32 times. If I add all these up, this would equal 32. It says, for which colors does the experimental probability match the theoretical probability? Okay, so the experimental probability is this right here. This is what actually happened. Okay, but we want to know what is the theoretical probability. All right, so I see that white is like a 1/4 section. Yellow is also 1/4, and then I see that red, blue, green, and orange are 1/8 size sections. So we're going to need to figure out the probability of each thing happening here. So since I have so many 1/8 size sections, I'm going to do 1/8 is equal to x over 32. Well, I know that if I just multiply by 4, I get to 32. So that would be x would equal 4 times. So orange, green, blue, and red should be 4. That would be the theoretical probability. Now let's look at these. So green matches that. Okay, green is 4. Orange is 5, so it didn't match. Blue was 4, so it did match the theoretical probability. And red says 2, and it should have been 4 as well. All right, so now let's check the other. These are 1/4 sections, so let's do 1/4 equals x over 32. And we could cross multiply and divide here, but I noticed I could just multiply by 8. So x would equal 8. So this would be 8 and 8. Okay, so 4 and 4 make 8. 4 and 4 make 8, and 8 times 4 would be 32. So this is another way to kind of think about this. Now, white matches because it is 8, but yellow is 9. Okay, so it says, for which colors does the experimental probability match the theoretical probability? Well, I would have to say white, blue, and green. Because, you know, according to the theoretical probability of getting 1/8 of the time red or blue, we're supposed to get 4 out of 32. 4 out of 32 equals 1/8. All right, so it does actually match. Our theoretical probability and our experimental probability match. Okay, this is kind of what we always say, it's a prediction, so we wouldn't expect it to match, but sometimes it actually does. All right, if the die above is rolled 300 times, predict the number of times it would land on a multiple of 2. Okay, so if it's rolled 300 times, that's a total. So I'm going to say that's on bottom. Predict the number of times it would land on a multiple of 2. Okay, so my multiples of 2 are 2, 4, and 6. So that's 3. All right, and my total down here is going to be 6 because it's a 6-sided die. Now, one thing I know about 3/6 is that I can actually simplify it. So I'm going to say x over 300 equals 1/2. Okay, so now I'm going to cross multiply. I'm going to say 2x equals 300. I'm going to divide both sides by 2. Get x equals 150 times. All right, so I would expect that the die to end up on a multiple of 2 about 150 times if it's rolled 300 times. So, you know, about half the time, which makes sense because it should be 1/2. In an experiment, a 6-sided die is rolled 84 times. The results are shown below. So these are the experimental results. For which number or numbers does the experimental probability and match the theoretical probability? Okay, so now in this case, all of them are going to be the same, 1/6. Okay, so we want x over 84. Okay, so every number is equally likely, so 1/6. So since all of them are equal likely chance, we can just do 1/6 equals x over 84. Let's cross multiply. So we get 6x is equal to 84. Divide both sides by 6. And we're going to get x. 6 goes into 8 once, there'd be 24 left over. 6 goes into 24 4 times. So every time where it's a 14, they match. The experimental probability matched the theoretical probability. So for which numbers or numbers does the experimental probability match the theoretical probability? We would say 1 and 5 match. Okay. So remember, theoretical is what should happen. Experimental is what actually happens. They don't have to match. You'll notice most of them didn't. But these two actually did land on the theoretical probability. Peter is interested in designing an experiment to test the probability of tossing a certain number on a fair cube. He will toss one cube 100 times in a row, so that's our total, and count how many times the cube lands on the number 4. What is one aspect of this experiment he can change to make the results even more accurate? Okay, so he wants it to land on a 4, which is going to be 1 out of 6 times. So again, here he's interested in designing experiments to test the probability of tossing a certain number on a fair cube. He will toss one cube 100 times in a row and count how many times the cube lands on the number 4. What is one aspect of this experiment he can change to make the result even more accurate? So even more accurate to what? Accurate to the theoretical probability. Okay, so how do we get this to be closer to 1/6? We know that if we do it 100 times, we should get a certain number be a 4. Okay, so it says he can use a number other than 4 to count. Well, that's not going to change anything really. He can time the experiment. Well, time it doesn't matter. You can roll the cube as fast as you want. He can toss more than one cube. Well, if you toss more than one cube, let's say we did 2 cubes, then we would only have to do it 50 times to get 100 rolls. So that doesn't really change anything. Then you can toss the cube more than 100 times. So if you're not quite equal to your theoretical probability after 100 times, you could maybe do another 100. You could do 200, or you could do 500, you could do 1,000, or you could do 100,000 times. So this is something that he could do to the experiment in order to get the results more accurate and closer to his theoretical probability. And that's kind of the idea, is the more trials you do, the more experiments you do, your experimental probability should get closer to your theoretical probability. We would never say or never expect them to be equal, but in order to get them closer, you should do more experiments. So Ralph put 10 socks in the dryer. 4 of the socks are white, so I'm going to say 4 are white. 4 of the socks are black, and 2 of the socks are blue. If Ralph randomly draws 1 sock from the dryer, what's the probability it would be blue? So we would have 2 out of 10, which equals 1/5. So he has a 1 out of 5 chance that he's going to grab a blue sock. There are 50 students in the auditorium. 18 of the students are in 4th grade. So I'm going to say 18 are in 4th, and 18 are in 5th grade, and the rest are in 6th. So 18 and 18 makes 36. 36, we would have 14 students in 6th grade. That would give us our total of 50 students. So it says if a student is chosen at random from the auditorium, what is the probability the student will be a 5th grader? So it would be 18 out of 50. And then we can simplify those. We can divide by 2 to be 9 out of 25. So you have a 9 out of 25 chance of being chosen if you are a fifth grader. Again, we will always simplify to the simplest terms. So 18 out of 50 works, but 19 out of 25 is the correct